And we're live.
So here we go. My favorite student. Okay. So key ideas that we've talked about for this particular quiz. I'm sure somewhere along the way I'm going to be asked to just calculate momentum, which is mass times velocity. And I'm going to recognize that change in momentum can be written in two ways. It can be written as force change in time, or like any change in, it can be final minus initial. And I'm going to mix and match and see what I can get there. Let's see. How much momentum, number one, does an 80 kilogram mass have if it's traveling at 22 meters per second? Okay. Mass times velocity, 80 times 22. Can I do it in my head? It's going to be 160 plus 16. 176? No? I'm way off. No, I'm 1,760? Yeah, it's off by a decimal. 1,760 units, kilogram, meter per second. Forgot to carry the zero. A motorbike has a mass, check. Constant force acts on it for 58 seconds. Okay, right now I'm thinking force times time, but maybe not. Bike's initial velocity is 23. Its final velocity is 52. Actually, I'm not thinking force times time. A asks, what's the change in momentum? So change in momentum, I think I'm going to use final minus initial, which is going to be mv final minus mv initial. It's going to be mass v final. I don't see a change in direction mentioned anywhere, so I don't need to let one of these be negative. I think we're good. Minus mass v initial. Hello, there it is. Looks like the change in momentum is going to be 220 minus 50, minus times, I didn't do times, I said it wrong though. 52 minus 220 times 23. I got two timeses in there. That's going to be a syntax error. Delete. Do you get 6,380? No? Yes? Yep. 6,380 kilogram meters per second. What's the magnitude of the force that acts on it? Okay, now I think I'm going to say force times change in time also equals change in momentum. I think the force is going to be change in momentum divided by the time. It's going to be 6,380 divided by 58 seconds. It's going to be, holy smokes, it works out evenly. That tells you Mr. Kamosi made up this question. 110 newtons. He's better at mental math than I am. I don't care enough to make them work out evenly. One mark. Water skier is moving. Let's go. What impulse is needed to bring him to a rest? What the heck is impulse? Oh, so that's going to be, you know what? It's going to be final minus initial, not force times time, because I don't see a force or a time mentioned in the question. And because it says to rest, the final momentum is going to be 0. Stopped. Minus mass v initial. It's going to be 0, take away 80 times 18. Can I go negative? Can I go 80 times 18 in my head? 80 times 10 is 800. 80 times 8 is going to be 604. 1,440? Yeah. Is that right? 1440? Kilogram meters per second. If the impulse is provided by the water, which I think it is when you're water skiing, it's the water that brings you to a stop, exerting an average force of 270 newtons, how long should this force act? Okay, so now I'm going to say impulse also equals force change in time. I guess the time is going to be the impulse divided by the force. It's going to be negative 1,440 divided by, why is this technically wrong? I'm going to have negative time. Wait a minute. if the change in momentum is in the negative backwards direction, that's because the force is also in the negative backwards direction. Now, or if you had just, Emma, said, look, I know the answer is positive, and you hadn't bothered putting any negatives in at all, I'm good with that. But if you're telling me the answer is negative time, I would take a half mark off. But Einstein said that we can go backwards. No negative time. Do you get 5.3 seconds? Is that about right? Water skier, let's go. 1, 2, 3, 4, 5. Yeah, okay. They kind of coast for a while and then they stop. Fair enough. 18 meters per second, that's, I think, reasonably quick. 1 mark. Turn the page, you say? I think so. Hey, how many marks is 4A worth? I bet you there's going to be a little tricky or something I got to be careful with. Or maybe it's a 2-step. I don't know. Halen, what do you want me to find in 4A? What do they want me to find in 4A? It's the second. No. What do they want me to find in 4A? Second word. Sorry, what? What the heck is impulse? Oh, they really want me to find change in momentum, so I'm going to write that down. Aren't I? Okay. Speaking of impulse, okay. Oh, you know what? I don't think I'm going to go force times change in time because they didn't give me a force or a time. In fact, in part B, they're asking me for the force. I think, Halen, I'm going to go final minus initial. It's going to be mv final minus mv initial. McKinley, my friend, what's the mass? Be careful. Don't say 170. 0.17 because it's grams, so 0.17. What's v final? Okay. Minus, what's the mass? 0.17. What's V initial? Ah, okay, so he decided to let west be positive and east be negative. Perfectly acceptable. Or you could have let east be positive and west be negative. We'll all have the same magnitudes and we'll interpret our directions consistently. So negative 22. By the way, I probably would have let initial be negative as well, only because I love the fact that I get a minus minus, which is a what? And anytime I get rid of negatives, I'm less likely to make dumb mistakes, so that's good thinking. I would do it that way, even though normally east to the right normally is positive. I think just this once I might have said, if initial is negative, I got a minus minus, which is a plus, so to speak. I'm going to get 0.17 times 43 times 43, take away 0.17 times negative 22. Here's the idea. Here's the key. So I get 33.8 kilogram meters per second. Direction in the positive direction. Am I wrong? I did?
You put 0.7.
I put 0.7. Sheesh. I should have caught that. I get 11.05. Is that better? 11 point, I'll go 11.1. 11 point. But it's positive, yes? So that's in the positive direction. What did you let be the positive direction? You let east be the positive direction? You let west, which one? West? You're sure now? Because I'll give you a chance to change. You want to phone a friend? No? Got a lifeline? Okay, west. So if you said that magnitude and west, now if you let west be negative and east be positive, you would have just had a negative on your calculator and you would have interpreted that in the negative direction, which was I happen to let be west. As long as you're consistent, I'll take either option. Otherwise, if you got that right, 2 out of 2. Otherwise, I'd probably go a half mark if I saw that, a half mark if I saw that, a half mark for the magnitude, and a half mark for the direction. Something like that. Now they want me to find the force. Okay. Force change in time also equals impulse. it's going to be... By the way, technically, I didn't ask for the force. What word did I put in front of the force? Average. I don't think a hockey stick, the force is constant all the way through. We saw a couple of weeks ago that high-speed video of the hockey stick with the stresses and the bending. I don't think, Rob, it's a constant force. So I'm hedging my bets as a physics nerd and saying, I think we're just finding the average force, but okay. That's, again, me just being really fussy, right? Seen that before? Shut up. Divided by 0.025. 442 newtons? Direction, west, but I didn't exactly specify a direction. Anyways, I would probably go something like this. 1 mark for that, half mark for that, half mark for the answer. Baseball, thrown due east. Struck by a bat, rebounds due west. The bat is in contact with the ball for that long. The average force applied by the bat is that much. Find the impulse. I think I'm going to use force change in time. Why? Because they gave me a force in newtons and a time in seconds. 20,400. 7.5 times 10 to the negative 4. Is that right, Mr. Dueck? Check, 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 check. Do you get an impulse to 15.3? What? I would take kilogram meters per second, but since I use force times time, I'll write it as Newton seconds. I'd take either. Find the final velocity. Ooh, this is a little different. Suggestions? Any thoughts? How the heck can I find V final? Which equations is? Since I know that delta P is 15.3. Okay, I want to get that by itself. Keep going, Atla.
You add the MVI to the other side, and then divide by n.
So you're saying the final speed of this baseball is going to be 15.3 take away 0.15? Why am I wrong? I am. For me? Oh, isn't it plus there? Why am I still wrong, Mr. Dueck? Let me see here. I let this be positive. This is positive because I think this, in terms of direction, is to the west. I kind of, sort of think I need to do that. I kind of, sort of think I need to let my initial velocity be negative. Don't I? There's a change in direction here. I got to be careful here. Okay? In fact, what I really should have done before even starting is I should have said, I'm either going to let east be positive and west be negative, or west be positive and east be negative. This gave me the magnitude of the force. I'm not sure here. Let's find out. Let's crunch the numbers and interpret. What direction is the final velocity? It's got to be west, okay? If that there is positive, so if I let that be positive, if I have this, can I possibly, look at the numbers, end up with a westward velocity? I can from those? Because what's westward velocity going to be, positive or negative? Can I possibly go positive plus positive times positive divided by positive and get negative? So something's wrong with me. So either I have to let the final force be negative in this equation to show west, or I have to let this be negative and let west be positive. I got to do something. Got to do something. Otherwise, there's no way this can work. By the way, how many marks was part B worth? Oh, maybe this was Y. I think it's going to end up being, so I'm going to let my incoming be negative and my outgoing be positive, and I'm going to end up getting then, I hope a positive answer here. Uh-oh. I did times instead of plus, Mr. Dueck. Let's try that again. Okay. It heads west at 63, not something else. Now, the other thing, I'm going to write this down, 63 meters per second west. Or what I could have done is I could have said, if this is positive, okay, I would have then said, what direction is the force? What direction is the force? In the same direction as the ball is coming in? You've seen baseballs hit. No, you're hitting against the, so I should have called that negative. That would have given me a negative there. That would have given me a negative there. And a positive there. And I would have got this. Negative 15.3 plus 0.15 times, good gosh, my pen is there we go, 3 plus, come on pen, 0.15, so far so good, times positive 39 divided by 0.15. The negative, because I let east be positive, that would also tell me west. So if you slipped up on that, in other words, if you got the wrong magnitude of velocity, if you got that as an answer, which, by the way, is pretty fast. That's taking off at over 250 miles an hour. That's pretty fast. I'll give you 2 out of 3 on this question, okay? Otherwise, I would probably go something like this. 1 mark for that. I would probably go a half mark if I saw, actually, you know what? I'd probably go a half mark for that, half mark for that, 1 mark for that, 1 mark for the answer, and I would probably save, I'll say minus a half for wrong direction. In other words, if you got east for some reason, or if you got 141 meters per second, you can get 2.5 out of 3. That's a tricky one. That's about as tricky as they'll get in terms of the impulse change in momentum in Physics 11. Direction, direction, direction. Give yourself a lovely clear score out of, count them, a 13, please. And then pass them inwards. So picking up where we left off. Curling is a great example of conservation of momentum. The only thing with curling is, in real curling, the masses are identical and tend to cancel. So this time I said it's an identical curling stone, but you're going to see most of the time, for some reason, just to make the math interesting, I make the rocks, the curling stones, different masses. But the ice part of it is nearly frictionless. It is very nearly, in real life, a closed system. Emma, there is a tiny bit of friction. Okay, fair enough. But it's about as close as we ever get in our physics world, where normally I'm saying we're ignoring this, and this is pretty good. So a curling stone traveling due east. I'll draw little compass rose. It's traveling due east at 2.6 meters per second. Check. Strikes an identical stationary curling stone. After the collision, the first stone is moving east at 0.65 meters per second. What's the final velocity, magnitude, and direction of the second stone? Jake, what word did I underline? You know what this is a job for? So what was our little thing? if there's a collision or an explosion, this is a job for conservation of momentum. Okay? Because we're at the point now, so listen, free body diagram, we're at the point now where you've got about 7 or 8 physics tools. What do I use? And I'm trying to give you, this is how my brain works. What, it's a collision or explosion? I'm starting out in momentum. It may not work, but I'm certainly going to start out there. Okay? They're asking about forces and friction, probably a free body diagram. Change in height, change in speed, probably conservation of energy, especially if they use scalar words. In other words, if it said find the final speed, I might start thinking scalar. But here they said find the final velocity. That's a vector approach, momentum. So how did we write that? Shaq, this is a bit new. This is our abbreviation. I want to write as short as possible the total momentum before equals the total momentum after. What was our symbol, our abbreviation for total or sum of? The little Greek sigma. The sum of all the momentum before the collision equals all the momentum after the collision. Darian, prepare yourself. Okay. Before the collision, what's moving? Mass 1, mass 2, and hopefully it's starting to sound somewhat repetitive. Our approach will be. So before the collision, what's moving? Mass 1, mass 2, or both? Mass 1? Momentum 1, initial. Wham! They collide. My aim was off. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? So momentum 1, final. Momentum 2, final. Now I've got my setup. Is there a change in direction? I'm not sure. I'm going to let east be positive. And Manny, if I get a negative answer, then I'll know change direction somehow. Speaking of, Manny, what are they asking me to find? Which is going to be hidden, of which? You know what? They're asking me to find the V in there. Let's break momentum. Let's do our substitution. P, momentum is what times what? Mass times, so we can say this is going to be mass 1 V1 initial vector bar, to remind myself, be careful with direction. Mass 1 V1 final vector bar, to remind myself to be careful, plus mass 2 V2 vector bar. Manny, what did you say we're trying to get by itself? Which one? There's several V finals. V2 final? That guy. How would I get that guy by itself? Do you need the notes? Yes, you do. Say, yes, Mr. Dueck, I do. Let's keep going now that we have our notes. Kai, how would I get V2 final by itself? Okay, so I'll make a little note here. I'm going to minus that to that side. So I'd get this, M1 V1 initial minus M1 V1 final. Keep going. Is that okay, folks? Yeah? Minus the non-V term that I'm interested in over, and then divide to get the V that I am interested in by itself. Now, in this question, because M1 and M2 are all identical, some of you who are spotted that may have noticed, I could have canceled out the masses. I'm not going to, because usually they won't cancel, because usually it's a car hitting a truck, or a hockey player hitting a smaller hockey player or whatever, but you could have in just this once, yeah. V2 final is going to be mass 1. Oh, I got to scroll up. 18. V initial, 2.6 minus 18. V final, 0.65. All over mass 2. Do you see how there's an 18 and everything? I could have canceled it, but final velocity of object 2 is going to be I can do this in my head. Of course I can, because the 18s would cancel, so you really just end up with 2.6, take away 0.65. It's going to be 1.95, right? Yeah. That was dumb of me. Could have done that right away. Units. Meters per second. Direction, based on our convention for this question. What direction must this be? I heard someone say west. I heard someone say east. One of them's right. If it was west, what kind of an answer would I have gotten? Did I get a negative? Nope. I did it in my head, but it's positive. So east, because that's what I decided was going to be positive. And that's really one of the common mistakes. Emma, be consistent in your question, okay? Especially as soon as you notice compass directions or the word rebounds, you better decide which way I'm going to let be positive, imagine it, which way I'm going to let be negative, imagine it, and then be consistent for the rest of the question, and then translate the negative or positive to get the direction. I guess what we're talking about here then is a collision like this. Look up. We have a curling rock standing still, one incoming. The second one moves off faster. The first one does keep moving, but not very fast. Yeah, I've seen that happen in curling before. Another good example of collisions is in pool, in billiards, right? Although in billiards, most collisions are not straight on. They're also at angles like in curling. So we actually look at them more in Physics 12 because angled collisions are way tougher, but cooler. A 22-kilogram curling stone is traveling due east at 3.2 meters per second. Check. Strikes a 16-kilogram curling stone that's moving due west. Okay, now we got two people that are having fun after the match. They're smashing stones towards each other. That's a collision. You know what that's a job for? Conservation of momentum. Okay. The sum of all the momentum before equals the sum of all the momentum after. Halen, by the way, what are they asking me to find? Which one? There's two. Of which? Okay. Before the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Separate? Okay, so let's go momentum 1 initial, momentum 2 initial. Bam! They collide. Got you, Kurt. After the collision, I should have timed it just when you were starting to swallow the candy because that could have been a bit of an adventure, right? Or whatever it was you were unwrapping there. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? Ooh, okay. Momentum 1 final plus momentum 2 final. And again, Kai, I won't take marks off if you don't put the vectors on there. But to me, every time I do that, I'm reminding myself what? Be careful with directions. Especially, I do see an east and a west here. Let's be consistent. Let's decide right now, which direction do you want to be positive, east or west? I don't care. So I'm going to go like this. Above the word east, I'm going to put a plus VE for positive. You could write out, by the way, Rob, east is positive, but you've already clued in I'm lazy. I want to be organized, but lazy. Above the word west, I'm going to put a little minus VE. If I get a negative answer, west. If I get a positive answer, east. It looks like what I'm trying to find is hidden in there. Let's break these apart. How can I write momentum? Momentum is what times what? Mass times velocity. So this is going to be mass 1 V1 initial, mass 2 V2 initial, mass 1 V1 final, mass 2 V2 final. Okay. I'm not used to having 4 terms, but it's only uglier. I don't think it's going to be that bad. And again, as Halen pointed out, there's what we're looking for, that B. Okay, how would I get that by itself? Okay, I'm going to minus this to that side. And then, well, let's see. That's going to give me M1 V1 initial M2 V2 initial equals, no, not equals, Mr. Dueck. You're minusing, minus M2 V2 final. That equals M1 V1 final. Wait a minute, how can I get V1 final by itself? Are the masses identical this time? They are? No, so I can't, even if I wanted to, I couldn't cancel the m's out this time. That'll leave enough room? Yeah, I think so. I can work down. So the final velocity is going to be, well, M1 is 22. I'll stick that on the bottom. No, it's not M1. It's M1. 22. What's V1 initial? I've scrolled down. What is it? 3.2. Positive or negative? Positive. Plus, I've scrolled down. What was mass 2? 16. What's V2 initial? To the west, negative 1.6. Take away, M2 was 16. What was V2 final? And be careful with signs. Is it to the west? Okay, now I'm confused. I better go look. It's 2.4? And to the east? So positive? Kyle, is there more than one number on the top? Better put the whole thing in brackets and then divide by the mass. And now, again, replace curling stones with car crashes and larger masses, and you're starting to be able to analyze or model or simulate car wreckage. The only problem with cars is as soon as they start to move together or apart from each other after the crash, they're also skidding. I'd have to have some way to include the fact that we're losing energy to friction. So it's a more complicated model. But if you combine what we did last unit, forces and this, you can almost get it with Physics 11 skills. The only problem is this wouldn't handle something at an angle, only a head-on collision. I'm going to get 22 times 3.2 plus 16 times negative 1.6, take away 16 times 2.4, divided by 22. Do you get 0.29? Positive or negative? Direction then. Capital E or east. Okay. Thumbs up, Anthony? Thumbs up, Kurt? Yes. Leave it away. A 45-kilogram boy and a 60-kilogram girl are standing in the middle of a frozen pond. Ooh, ice. This will be like a closed system. Cool. The boy gives a girl a push, as shown, and she moves off with a speed of 2.4. What's going to happen to the boy when he pushes his sister, who has more mass than him? If he pushes her forwards, what's going to happen to him? Going to go backwards. In fact, if I had somebody here who felt fairly athletic, we could bring in rollerblades and have two people play catch with medicine balls. And you would notice that if you're on rollerblades and you try chest passing a medicine ball forwards, you automatically move backwards because your initial momentum is 0, your final momentum has to be 0, and the only way to do that is to have something move in the opposite direction. Did I have the outer space question? No. Okay, I'll bring that up later. So let's try this one. Is there a collision? Well, this is an explosion. A really slow, controlled explosion, but all an explosion is when stuff moves apart from each other at velocity. This is an explosion. So you know what that means? This is a job for? I'm going to start out by saying the sum of all the momentum before equals the sum of all the momentum after. Before the explosion, what's moving? Mass 1, girl, mass 2, boy, or both? Neither. Neither. So what's my initial momentum then? Okay. Boom! After the explosion, after the push, what's moving? The girl, the boy, or both? Stuck together or separate? So that's going to be momentum girl, momentum boy. I could go mass 1 and 2. I'll go G and B, girl and boy. You know what, Mr. Dueck? What? This is an awful lot like when you were firing that rifle, Mr. Dueck. We had 0 equals momentum of the bullet, momentum of the rifle. Yeah, it's a slower explosion, but it's the same physics. Jeff, what are we trying to find? There's more than one. Which one? They're both final. Which one? Yes, you're overcomplicated. So what do I want to find? Velocity of the boy. It's going to be hidden in there, but I better break it up. What have we said? Momentum is what times what? Mass times velocity. So 0 is going to be mass girl, V girl, plus mass boy, V boy. Oh boy. No, V boy. Okay, let's get V boy by itself. How? Minus that to that side. That's going to give me negative, oh, change colors, Mr. Dueck. Negative mass girl, V girl. Mass boy, V boy. Oh, wait a minute. I haven't quite got the mass, sorry, the V by itself. The final speed of the boy is going to be negative 60 times. Do we have 2 different directions here? Okay, so let's decide. Look at the girl. Do we want to let that direction be negative or positive? I don't care, but we now have to decide and be consistent for the rest of the question. So looking at the girl, she's traveling to the left or she's moving backwards. Do we want to let that be negative or positive? Negative. You want to let that be negative? So let's make a little note right above where the V is. Let's say that this is negative, positive. So if I end up with a positive answer, it's going to be to the right. If I end up with a negative answer, it's going to be to the left. Could have let it be the other way around too, and it's perfectly fine. So for V girl then, I'm not going to put in 2.4. What am I really going to put in? Divided by mass of the boy, which was 45. I think I can do this in my head because 60 over 45 is the same as 4 over 3. So it's going to be divide by 3, which is going to be negative 0.8 times 3.2. Double check me. Yeah? Direction. In the positive direction, which is which direction in my picture? Right. Or east. Okay. Hopefully what you're starting to see, Darian, it's really the same thing over and over. We have to tweak it, but as long as I start with the law of conservation of momentum, everything before equals everything after, wham, they collide, and then I say, okay, what was moving before, stuck together or separate? What was moving after, stuck together or separate? It's not plug and chug, but close. Hey, Darian, what does B want me to find? What's another word for impulse? Change in momentum. It is also force times time, but I don't see no force and no time, so change in momentum. I'm going to say the impulse is going to be momentum final minus momentum initial, which is going to be mv final minus, wait a minute, what was this boy's initial momentum? So it's going to be 45 times 3.2. It's going to be the same as 90 times 1.6, which is going to be the same as 90 plus 154? No, 144. 144? Yeah. I'm on a roll. That's pretty good. Units. Kilogram, meters per second. What's the impulse of the girl? I could crunch it. I could go change it. Anything is final minus initial. But if the boy gained 144 kilogram meters per second, what can you say? Or instead of negative and positive, you could say for the boy to the right and for the girl to the left. But she lost momentum. That's why we are able to start with 0 and still end with 0. Oh. If the push lasted for a quarter of a second, for 0.25 seconds, with what average force did the boy push the girl? Okay. I think now I can say change in momentum also equals force change in time. The force is going to be impulse over time. What was the impulse? 144. Time, 0.25. It's going to be 144 times 4, which is going to be 400 plus 160, 576? Newtons. So far, so good, Manny? E. Ooh, a little bit of review. What does E want us to find? Work. Well, my first thought was to go like this. And the reason my first thought was to go like that is, what did I just find in part D? Force. I don't have a distance. Now, maybe there's enough that I can calculate a distance, but then I said, well, the other definition of work was change in potential energy plus change in kinetic energy. I think that's more promising. Did they, look at the picture, did they change height at all? So did they change potential energy at all? Change in kinetic. What's change in anything? This is going to be, hey, wait a minute. What was their initial kinetic energy? They were both at rest. So I think the work is going to be the final kinetic energy, but of both of them, because they both started moving, and that all came from the boy. It's going to be the kinetic energy of the girl and the kinetic energy of the boy. He provided it all. That's how much work he had to do to get both of them moving. Hey, what's kinetic energy? A half Oh, so this is going to be a half mass girl v girl squared plus a half mass boy v boy squared. Oh, didn't want to press that one. Wrong button, Mr. Dueck. I want this one. Thunk. A bit more room. All righty. Well, let's see. 0.5. What was the mass of the girl? 60? What was her, careful, speed? Scalar. I don't need to put the negative velocity in, just her speed. 2.4 squared? Plus 0.5. The boy was 45, right? And what was his speed? Oh, we calculated that, didn't we? 3.2 squared. Now, while you're crunching the numbers, we might have, Halen, been able to do force times distance, because I do know that t was 0.25 seconds, according to part D. I do know that VI was 0. Although VF is different for both of them, isn't it? So maybe I couldn't find acceleration and then use that to go F equals ma or at distance. You know what? I think this is my best strategy for this multi-mass, multi-body problem. Do you get that? No? Am I wrong? Yeah, I am. The times didn't show up. That better? Do you get 403.2? Okay. I'll just call it 403 joules of work. The boy applied a force over distance to both of them, force compares, and therefore he changed their energy state. But he didn't change their momentum state, because their initial momentum was 0, their final momentum still 0. That's that one, and then I talk about types of collisions, right? We're going to go to types of collisions first, and then we're going to come back to this one. There are two main types of collisions where objects stick together. Some car crashes. When a football player tackles and holds on to the ball carrier. A dart hitting a dartboard. Person catching a ball or a projectile. Okay? The fancy physics word for that is, come here, Mr. Dueck, inelastic. In an inelastic collision, in an inelastic collision, objects stick together. And I'll tell you a way to remember that in just a second. The second type of collision is where the objects bounce off of each other after the collision. Curling, billiards, baseball hitting a baseball bat, body check in hockey, some other car crashes where the objects don't stick together. The fancy word for that one is elastic. We have elastic and inelastic, and here's how I remember this. If I said to you, get me an elastic, what do I mean by an elastic? What are we referring to? Rubber band. I think elastic, rubber band, bounce apart. That's elastic. Something that's elastic is rubbery, it bounces apart, doesn't stick together. Inelastic, I always just remember, is the opposite of elastic. So Kurt, if the question says two objects collide together inelastically, you'll see my eyes glaze over for a second, and I say inelastic, that's not elastic, that's not rubber band, that's not bounce, that's not stick together, that's not bounce, stick together, so it's not bounce apart, stick together. Those are two types of collisions. We will use those words sometimes in questions. In other words, when you've heard me ask, stuck together or separate. The question may not blatantly say, but it may say collide inelastically. stuck together. Collides elastically. Separate. Here we go. A 30-gram bullet moving at 250 meters per second strikes a 5-kilogram wood block at rest and sticks into it. That's a collision. If the bullet and the block move off together, write a momentum equation. You know what? I think I've done enough of these, although it's kind of cool to shoot something. I'm going to say, and I want to get you started on the homework, because with Easter weekend, I don't want you to have a whole bunch of homework, so let me hand this out. Take a look at what I just gave you. So the first sheet that I gave you is called Conservation of Momentum 1. Why? Because it's the first conservation of momentum sheet. Okay. I think you can try neutron works. Yeah. You know what? Every question here is fair game, and you should find scrambled answers on the bottom. So that's 12 questions. And then the second sheet that I gave you, conservation momentum 2. I'm not going to assign every single question here. This first one is actually, I cover this in Physics 12, but I'm curious to see if you can kind of figure it out. So see if you can figure out number 1. If not, I'll talk about that next class for sure. Number 2, this was my limit with stick art. I was trying to show before and after collisions. So here I'm trying to show they're stuck together. Here I'm showing they're not stuck together, they're separate. Here it's moving, here it's at rest because there's no velocity arrow. So I wanted to give you just a whole bunch of practice questions, all right? So number 2, try that. That gives you pretty much every possible situation. He'll figure it out. Thank you. Cannonball, you know what? We've done stuff like that. I'll go meh. I'll go baseball instead. So number 4, yes. I skipped 3. Number 5, I'm going to put a star next to. What are they asking me to find in number 5? Okay, see if you can figure out how to get m by itself. This one's going to be tricky. In fact, this one is a little more Physics 12 than anything. Okay, so that's why I put a star next to it. I nuked it. I might do 7 because it's a good car crash. Let me see. Hang on here. So I'm going to say also with a star next to it. These are nasties. One is nasty. 2 to me is lots of practice. But after that, it gets a bit tricky. Try 7. What's the speed that they gave you for the car? Kilometers per hour. So make sure you divide by 3.6 to get meters per second. It's going to be almost exactly 1 meter per second. Not quite. But now I'm also giving you some friction and asking to find a distance. So for part B, I think it's a time for a free body diagram. You'll need to find the acceleration, and then V final is 0. You can find distance, and then C impact force. I'm really assigning number 7, Kurt, because we're towards the end of the year. I want to start to try and stick some extra review stuff as we're getting close to the end of the year. Now, the nice thing is, one of the things I like about Physics Dane is we've been flogging D and V and I and T pretty much all year long anyhow, even though I did that in the very, very first unit. So I'm only going to be, as we get towards the end of the year, reviewing more recent stuff, which is good. So 7 is fair game, but nasty. I'll pass on 8. 9 is fair game. 10 we talked about. So you may have seen large yellow containers on the highways at exit ramps. These containers are filled with sand or water. In our climate, almost always water. In drier climates, it might be sand because the water might evaporate. Newer containers have a loose top half, even resting on the bottom. These are designed to protect cars that would otherwise hit solid concrete. They're called impact attenuators. How do they work? Sorry? Increase time of collision, lower t. So you guys don't need to do 10, we talked about it. You know what? 11 is kind of cool in that the velocities and momentums exactly cancel each other out, but nah, that's good enough. You got about 15 minutes. I think if you hustle, you can get all this done. I'm going to say if you don't get it done today, this is going to be due for Thursday, in that I don't want you to have on the 4-day Easter weekend homework. You can do it if you want to. I'm going to give you more stuff on Tuesday, but I won't officially collect this till Thursday.